Hello, everyone. Thanks for joining our webinar. We're going to start with hearing from the editors of the two sponsoring journals. Jeff, would you like to go first?
Sure. Thank you, Steve. Good morning, good afternoon, and good evening to all of you across different time zones. Welcome to the second joint webinar by ASME Letters in Translational Robotics and ASME Journal of Mechanisms and Robotics. My name is Jeff Ge. I'm the editor-in-chief of Letters in Translational Robotics. While the field of robotics and AI have seen an explosion of advancements, the path to practical applications, particularly in complex physical environments such as manufacturing automation, remains a significant challenge. Our journal and our webinar series focus on rigorous engineering required to turn foundational research in robotics into robust, real-world solutions. We invite you to contribute your most impactful work to our journal. And I would like to extend a sincere thank you to the invited speakers for such a timely and a relevant webinar, for sharing their insights into the future of AI-enabled robotics and manufacturing. I am grateful for the opportunity to be part of this conversation. Thank you.
Thank you, Jeff. And Andreas Mueller, our editor-in-chief of the ASME Journal of Mechanisms and Robotics, has a quick word to say.
Would like to join Jeff in thanking you all for joining this webinar. I think webinars are becoming more and more important because of the network that is internationally spreading out. And if you look at robotics, the journal is called Mechanisms and Robotics, and I'm honored to actually be since January the editor-in-chief of the journal. Mechanisms and Robotics, of course, is combining two disciplines, and robotics itself is an interdisciplinary research area. And the journal, I have to say, is following up another journal, which is mechanism design. But our journal is following up on mechanisms combining robotics, because the foundation for getting things really done is the embodiment. And robotics is, of course, an area where you can work on AI, and you name it, anything that has to do with software and what is now called intelligence, which in the past was called mechanical intelligence or just a good design. And our journal is based or is focusing on the theoretical development. And of course, it is a matured area, and that's why actually the ASME Letters on Translational Robotics spin off, because you do have prototypes that deserve to be exposed to the wider public. And so the combination of the two journals is a very interesting and truly very fruitful endeavor. So I guess people know the journal. Everybody is invited to submit their their basic research as well as applied research. It's of course a bit of a wide spectrum. You may think, what is theoretical, what is foundational, in the sense of an applied area, but anyway, it certainly fits into it. And if it doesn't fit, and this is what I would like to emphasize, the journals JMD, the Letters on Translational Robotics, and JMR, they have an agreement. If it doesn't fit, you're not automatically rejected. You're transferred to another journal where we deem your paper best fit. So don't hesitate, just send your good research, and we will find the venue for your paper to be published. And with that, I'm looking forward to the presentations of today.
Thank you, Andreas. And I'll be the last introduction before we get started. My name is Stephen Canfield. I'm co-editor of the newly founded ASME Letters of Translational Robotics. I want to welcome you today to our webinar. This is the second in our series entitled Using AI to Power Robotics and Manufacturing Applications. Over the recent past, artificial intelligence is everywhere. It's been driven by technologies and many organizations, but it seems like we see algorithmic advances. We see it in our popular media, But much less seen is this strong push for physical AI and particular applications to complex manufacturing challenges. We have with us today really the leaders in this field of physical AI applied to robotics, and I'm delighted that we have them and we're going to hear from them. The convergence of these technologies is transforming manufacturing. In today's session, we're going to explore how AI is refining industrial automation, explore underlying technical methods, emerging technologies, and discuss future applications. So to get started, I'm going to briefly introduce our panelists. Our first panelist and lead panelist is Dr. S.K. Gupta. He holds the Smith International Professorship in Aerospace and Mechanical Engineering Department and the Department of Computer Science at the University of Southern California, where he also founded the Center for Advanced Manufacturing. Prior to this, he was professor in the University of Maryland, College Park, where he was the founding director of the Maryland Robotics Center and Advanced Manufacturing Laboratory. He's a national leader in robotics. He served as the program director for NSF for the National Robotics Initiative. He's a guest researcher at NIST, currently a member of numerous technical advisory committees, including the ARM, the Advanced Robotics Institute, Advanced Automation for Robotics, and the National Materials and Manufacturing Board. He's a co-founder and chief scientist for Gray Matter Robotics, a company focused on robotic automation solutions for high-mix manufacturing applications, and he'll share more on that. Our second panelist is Blair Simmons. He's an automation chief engineer at Raytheon with expertise in all things robotics, automation, and system engineering. He served in multiple roles at Raytheon as lead automation systems, manufacturing, and mechanical design engineer. He received his MS and BS from University of South Florida. And our third panelist is Christopher Brown, a Boeing Technical Fellow in the Manufacturing Systems and Robotics in the Emerging Production Systems Organization within Boeing Technology Innovation in Tukwila, Washington. First, we'll have to correct my pronunciation on that. He's been with Boeing for over 20 years, providing automated solutions for various applications on composites, trimming, drilling, inspection. He currently runs the Production System Concept Center Research Lab, which specializes in high accuracy manufacturing for future aerospace development. His experience in integrating full-scale systems combining machine vision, sensor-guided feedback, dynamics, robotics, and control. He currently has 15 granted patents and another 10 pending, and has his BS degrees in aerospace engineering from Iowa State University of Science and Technology. Okay, so for our program today, we're going to hear from each of the panelists with an additional broader overview of the topic provided by Dr. Gupta, and then practical discussions relative to implementation, evaluation from Blair and Chris. Following this, I'm going to open up the floor for questions. I would ask that you enter your questions in the chat. You can do that anytime, and we'll pull from those questions for our panelists. Finally, we're going to adjourn right on time in 1 hour and a half, so that'd be 1:30 for our Eastern friends, 10:30 for our Western friends. Okay, let's get started. So with this, I'm going to turn the floor over. I'm going to turn the floor over to SK. Take it away, SK.
All right, just want to confirm that you guys can see my slides.
Yes.
Yep.
Okay, so I'm going to begin with a quick introduction to this topic and show you some examples. So robotics in manufacturing application, if you look at the entire landscape, you find out that robots get used a lot in mass production and driven by all the advances in automotive and electronic sector, where everybody is using robots in these mass production lines. On the other hand, if you look at the high mix productions, robots are not utilized that much. So overall, we want to investigate what happens in high mix and how we can put robots in high mix production applications. So the robot would get used quite a bit in mass production application have certain limitations which make them difficult to directly apply them to high mix application. So if you have a mass production application, you're going to be using this line for years, and therefore you have a lot of time to initially set up the line, program the robot, optimize everything, and then line will just run and keep doing the same thing over and over. And that gives you basically tremendous benefits and your return on investment works out. However, if you have a high mix production application, then this concept where you are going to spend months building a robotics line and then utilize it is not going to work, because the part that's going to be fed into the high mix setting will change frequently. And therefore, this idea that humans will come in, program the robot, optimize the cell is not going to work. So robots currently are largely used in mass production applications, approximately 3 robots per every 100 manufacturing workers in the US. High mix manufacturing application, part changeover needs to happen quickly. You're doing one type of part, then you need to start working on another part. And this transition has to happen very quickly. And you cannot also use part-specific fixtures. I mean, you have to use general-purpose fixture to hold the part, and therefore you cannot rely on the accuracy of fixtures to basically deliver you the right kind of performance. And robot have to be quite flexible, quite intelligent and smart to work in high-mix application. So reality today is that if you go look at a lot of high-mix application environment, lots of people are doing sanding, polishing, buffing, grinding, spraying, coating type of tasks by hand. And these are ergonomically challenging tasks. And people would prefer if bulk of this work can be done by the robots. If you look at the manufacturing challenge today, there are a significant number of jobs which are forecasted to go unfulfilled. There's a lot of labor shortage being reported by the manufacturing sector. As I mentioned before, many manual operations pose serious health risks for humans. Many companies are reporting significant backlogs. And when you have a large churn of human workers, you also start seeing the issues with respect to consistency of the quality, and therefore then you start experiencing rework and scrap and consumer waste type of challenges. So the right way to think about addressing this challenge would be to increase the level of automation in high mix applications. There are 3 key things which are currently driving progress in this overall field. One is availability of low-cost sensors. We have all kinds of sensors which at reasonable price now available. 2D vision, 3D vision, tactile sensing, force sensing. GPUs, which can actually make edge compute super fast as well as cloud compute super fast. And then all the recent advances in physical AI and generative AI are also giving basically new fundamental capabilities, which is changing the landscape quickly. If you look at the specific advances in robotics, people are beginning to now leverage stereo vision, force sensing, tactile sensing. Field is going well beyond simple position control. People are looking into impedance control, visual servo, shape control, all kind of new control modality. We can now do multi-arm manipulation where multiple arms can be coordinated, and therefore we can handle high degree of freedom systems. Mobile manipulation is here, which allows robot to go to work as opposed to work coming to the robot. And we have collaborative robots where humans and robot can work in close proximity of each other. So all these advances are creating new opportunities for us to utilize robots. So my own work is largely focused on human-centered automation. The idea there is that we want to empower people by giving them robotic tools so that the work which people should not be doing and do not want to do, is actually done by the robot. So we empower people, reduce their health risk, and boost their productivity. And that's a way to handle the labor shortage issue. Now, why do we need AI? So if you look at it, these challenges that are there in the production setting, the tool motions are complex, parts are large, people are often moving around them, so it's a loco manipulation problem. People are often making adjustments right when they're doing the process, and also even figuring it out what the right process is for a new material, new geometry, new type of tool takes effort. So again, old style, mass production style robotics would say we should spend weeks or months figuring it out and then program the robot to do it, but that's not going to work. So hope is that AI can actually go ahead and sense the part, build the model, generate the appropriate motions, and regulate the process, and even discover the right kind of process condition to process the part. So AI-powered robotic cells have at the bottom layer the hardware, the robots, the tools, the sensors. So, there's a tremendous amount of industrial robots available. So in manufacturing application, we can continue to leverage them. And as new hardware become available, we can use that. A lot of tools which are already available for grinding, welding, sanding, polishing type of tools, which we can all leverage it. And as I mentioned before, there are a lot of sensors which are available now. We can leverage them as well. So hardware-wise, a lot of good stuff exists that we can adopt from mass production. What we need is a layer above it. We want physical AI, which basically gives the robot capability to function autonomously. And then we need robot access to process knowledge so that they can basically go ahead and execute the operation. And this process knowledge can come from humans, and it can also come from robot conducting its own experiment. And at the top, we need the right kind of human-machine interface so that humans can interact with these cells. So I'm going to walk through a wide variety of representative AI applications, which will show you how people are beginning to use AI in these manufacturing applications. So I'm just going to go through this list quickly, show you some videos, show you some images. So here is a robotic cell built by Gray Matter Robotics. And the idea here is that this is a dual robot cell used for performing sanding on large part. The idea is that operator feeds the part into the cell. On a standard card, there's no part-specific fixturing needed here. Robot scans it, builds the model, segments the model, identifies all the features which are there using the scan data, and then perform processing. These parts are large. The cell does not assume that any CAD model exists. So it basically treats the part as a new part and then uses AI to figure it out, how to process it. So that's an example where AI is being used both in building the part model, segmenting it, doing the planning, driving the robot motion. Another interesting ways where people are beginning to use AI quite a bit is to learn from human demonstration. So people want to be able to learn from human demonstration where they want to see how humans were doing the task and then get that information transferred to the robot. And then robot can basically try to start from whatever humans were doing. And then hopefully after that, they can do their own experiment and do better. So here is an example where we have a fully instrumented cell in our lab. It's a full motion capture. We are capturing all the human motion, the way humans are doing it. And the tool is instrumented. So we are recording how much force human is providing. And then the idea is that could you transfer whatever you saw from human to the robot. And it turns out that you can use methods in inverse reinforcement learning to learn what humans were doing and get the sequence and motion right, and not only replicate the motion on the part on which the demonstration was done, but also on something slightly different. Here's a project that I did with Boeing and 3M, funded by Arm Institute. Chris was one of the major players at the Boeing driving this project. This is a publicly available video of that project. So again, composite layup, where robot picks up a ply, places on a tool, and then robot basically. Now, of course, some portions of this videos are blurred because of considerations of IP. But this gives you a general idea. Idea is, again, integrate perception and then very complex motions which are necessary to get this thing done. In real time, make appropriate adjustments. So in this case, once you place the ply, 3D imaging is used to inspect it. And then if there are any defects which are found on the part, or any bubbles, or any uncompacted region, then robot basically figures it out on its own, what kind of rework path it needs to go ahead and compact those regions. So this is showing that, how you can integrate all the rework capability and inspection capability in a cell. Here is a robot where we are converted a welder into a 3D printer. So here the idea is that basically a robotic welder can print 3D parts. And in this case, the challenge is that since we are using this rotary table, which basically tilts to eliminate the need for support structure, you really need to figure it out the right process parameters, because when you deposit the material, it flows. And if you don't regulate the process parameters, then you're not going to be able to form the right kind of shapes. So this again is an example where AI helps in processing the part the right way. We have also used AI quite a bit in detecting defects. So in composite, many composite materials are highly textured. Using traditional computer vision does not work. When you do the layup, you have all kind of basically bubbles and air pockets which appear as wrinkles. So you have to detect that, and then robot need to perform those repair operations. So we have basically built deep learning based pipelines which allow us to detect these defects and provide that information to the robot, that robot can intervene. And in this case, of course, training a deep learning model using only physical data is not possible. So we have built a synthetic data pipeline which allows us then to basically combine the physical data with synthetic data pipeline to generate enough data so that we can train a deep learning network to detect wrinkles very, very accurately. We have also done work with Amazon on basically picking up highly compliant packages and pack them in a compact way. So this is again showing how you can use simulation to build basically a online system where it can quickly pick up packages and pack them in a compact bins. Here's an example where again we are combining physical AI principle, where we are using physics-informed AI to build a model of screwdriving so that robot can perform autonomous screwdriving. Again, we are using computer vision along with the physics-informed AI, which allow us to basically figure it out where operation need to happen, monitor the screwdriving operation to make sure that if something is not working out well, then robot can make appropriate adjustments. So in this case, we are showing that robot can perform autonomous screwdriving in a high mix application. Oh, here's an example of a project which is just illustrating the machine vision capability. So here the idea is that a robot need to pick up these tools and store them away. So again, we're using computer vision to make sure that we can see the tools the right way. We figured out how to pick them up and store them. So in this case, we are using a spatialized gripper, which had basically a compliant pad made out of granular media to pick up these tools. Also, when you're performing sanding operation, you need to figure it out if the sandpaper has any life left. And if sandpaper is worn out, then you want to perform that tool change. So in this case, again, computer vision and AI being used to monitor the state of the sandpaper, and then you can trigger the appropriate tool changes, actually the media changes in this case. So this again allows you to run the system autonomously for many, many hours, because as the sandpaper wears out, robot can itself monitor its health and then take appropriate corrective actions. And also this is a good technology so that if something is not going right in the cell, if your process conditions are not right, the wear in the sandpaper also shows you that something is not right, and then you can take appropriate corrective actions. Also, when you deploy robotic cells, you want to make sure that you are running prognostics and health management system to ensure that your cell is behaving the way it is expected to behave. If something starts going wrong, then you can use digital twin to figure it out, that the physical signal that are actually coming from the cell and the signal your digital twin is predicting are diverging. So meaning that you were expecting certain kind of force based upon your digital twin production, and then your force sensor is telling you that I'm not seeing that signal, then you could intervene and take a guess at what might be going wrong. So imagine that you place the part in front of the robot and an operator forgot to clamp it. In the moment robots start processing it, part starts moving. So if that were to happen, a discrepancy will occur, and then you can use that discrepancy to figure it out what might be going wrong, and then bring the cell to a safe state, and therefore then you can ask human to intervene. So this is again an area where AI is being used quite a bit. A lot of time people are interested in controlling the robotic cells using gestures. So this is an area where human-robot collaboration piece, where people are beginning to use AI to make sure that humans can interact with the cells in a natural way. And AI is ensuring that gesture recognition accuracy is high, and people can do interesting things. Final example that I want to use is basically human detection. So when you build these collaborative cells, they're collaborative zones, they're non-collaborative zones. Collaborative zones where humans are allowed and human can go in there and can work there, where we expect humans. Non-collaborative zones are the zones where basically humans should not be there. So again, AI is being used for this complete monitoring of human presence, and then you can figure it out where humans are. And if it turns out that humans are present at a place where they should not be, then again, you can use to trigger appropriate safety alerts, and as well as, if necessary, shut down the robot cell. So this is another interesting area where AI is being used. So basically, overall, I gave you lots of examples of AI being used in manufacturing setting and different things that AI could do. So overall, people define physical AI in the context of manufacturing as AI which manages the behavior of physical systems. So unlike digital AI, where digital AI creates a digital artifact such as text, video, or an image. Physical AI produces a sequence of action recommendation, which a physical system then executes to achieve the given goal. For example, if you want robot to do sanding, you put the part in the cell, and physical AI is telling robot where to go, how much pressure to apply, what RPM to use, and what velocity to use to move the tool. Now, obviously, physical AI also monitors the cell state using sensors and then figure it out if there any intervention needed or any corrective actions are needed. To build basically physical AI, we need a 3 modality: imitation, which is basically we'll start with looking at how humans are doing it. So imitation learning is the technology that people use. And recently, a lot of interesting work in diffusion policies is fueling lots of new capability in imitation learning, where we can watch a video of a human performing a task, along with basically capturing the data from the tool part interaction, and then the robot can try to imitate that. Then the next layer is exploration, where robot can use reinforcement learning in simulation and also experiential reinforcement learning, where robot conducts experiment in the physical world. And that then allows robot to perform tasks even better than humans, or where human demonstration is not possible. And finally, reasoning. When you have long horizon tasks, then you need to figure it out how I'm going to chain my skills. So if I'm performing a complex assembly task, I may need to pick and place the part, I may need to reorient the part, I may need to apply adhesive dispensing, I may need to do screwdriving. So I need this higher level reasoning capability, which allows me to sequence things the right way, optimize the sequence, and then invoke the right skill at the right time. So ultimately, autonomous operation using physical AI in case of robotics becomes basically combining these technologies the right way. Right now, the architectures that are emerging basically is kind of ensemble of AI tools. At the lowest level, you have safe learning in physical world using basically some sort of control theoretic active learning type of approaches, where safety is super important, and you really want to make sure that whatever you do, you're not going to cause any part damage or tool damage. A level above that is where you're trying to learn intermediate decision making. Reinforcement learning in simulation is a very useful tool. And at the top level, we have high level decision making, and that's where large language model for tool manipulation as well as vision language model for tool manipulations are quite useful. And in work that I do, we basically chain these different technologies together to make sure that we build systems which actually work in practice. So people often ask, why we cannot do end-to-end learning. Why do we need these multiple AI tools? The analogy that I like to use is learning to play golf. I mean, you need to get probably an advice from instructor that speeds up your initial explorations. Then you can watch the videos of expert playing golf games. You can practice in simulator, and then you can go out and practice in real world. Each of these correspond to different AI technologies. So idea is that you want to have the right ensemble, because if you only try to practice in real world, it's going to take on your own. It'll take you a very long time. On the other hand, if you only get an advice from instructor and never practice, then you're not going to become a very good golf player. So the goal is that can you basically get the right modality, sequence the right way. And that's what AI, when we talk about these different layers that I showed you in the previous slide, large language models, visual language models, reinforcement learning in simulation, safe learning in physical world, correspond to. These are different modalities through which robot acquires skills and different kinds of skills. So in summary, it is now feasible to realize autonomous tool manipulation in high mix manufacturing. And using that, we can automate things like sanding, polishing, buffing, grinding, spraying, sandblasting, assembly, inspection, welding. So all kind of interesting things can be done. And a lot of commercial solutions which are coming out in this space as well. So surface finishing and treatment, welding, material handling, inspection, these are all now commercially available. You can start utilizing them in high mix applications. Robotic assembly is another exciting area where basically we are beginning to see more technology maturing taking place, perception which can identify and localize part, methods which can automatically generate robot motion, controllers which can safely execute assembly operation. So we are beginning to see a lot of exciting things happening in the robotic assembly space. So with that, I would like to conclude and would like to basically give the floor to Blair.
Alrighty, hi everybody. Let me switch this, make sure I'm on there. Can you see the actual presentation mode?
Flip your screen, Blair.
Open it again. All right, let's see here. How's that? Did that work?
Not yet. We're seeing that. We're seeing your view, not the print. There we go. No.
Of course.
There we go. Good.
How's that? All right, Eddie. All right, good afternoon, everybody. Good morning. Jump right in here. So Blair Simons, I'm a tech fellow and the chief engineer for Raytheon Connected Factory Intelligence Automation. So long title, but essentially we're talking about all things Industry 4. I've been in the defense industry for over 15 years, spanning everything from design, manufacturing, automation, Industry 4. So kind of really rooted primarily in the manufacturing space. And then kind of in the ground floor of what Raytheon has kind of organized as Industry 4, which includes the automation and robotics. And I do want to kind of use the next three kind of main bullets to emphasize or kind of demonstrate the approach that Raytheon takes to automation and robotics in general. And kind of the first thing is, as we start to integrate data, our big data, we start to integrate things like AI and new digital solutions. The line between, we just had traditional physical robotics and we had, maybe dashboards and metrics and digital solutions. Pretty hard line of demarcation in the past. Really now things are really starting to merge into a holistic and integrated system. So first thing I want to emphasize there. Second is, Raytheon's approach to Industry 4 in general also includes things like design for automation. So when we are talking about, robotics, we look at our designs and they were made for, hands. They were made for human dexterity, for, the human eyesight. But obviously, as we start to use more and more robotics, we may want to add things like, fiducials or grip points for robots to grab onto. So, really kind of using Industry 4 and automation to take a step back and look, how do we make the design of our products better and more automatable? I think the other thing to mention there is we invest real heavily in IRAD. And so pretty heavy in AI in manufacturing and robotics. Could include things like, the humanoids or, advanced CAD to path or advanced AI in robotics. So, pretty large investment on kind of the technology enablers. And then when it actually comes to, capital investment into robotics and automation in our factories, you can see some of the numbers there. Really pretty prolific across all of the different manufacturing sites within Raytheon. But really large investment from Raytheon in general, and that's only expected to continue to grow at really an exponential pace is really what we're seeing. So, robotics, it's a digital and physical solution. We invest heavily in IRAD and then in our capital investment. All right. For those of you that aren't familiar with Raytheon, just wanted to kind of give a quick overview here. And really the intent is when you think about, robotics and automation and the use of AI in the automation space, it's one thing to, build the same thing over and over. But if you really look at the Raytheon profile, you can start to see the breadth of products, and you can probably start to imagine some of the challenges that can cause for automation and robotics. So just generally, we have air-based systems, could be missile systems, effectors, surveillance. We have land systems and sea systems that are electro-optical systems. Obviously in the space realm as well. We do RF antennas, radars. Integrated air defense. So this would be like your Patriot system, strategic missile defense. This would be your standard missile product family where, sensors and interceptors for ICBMs, as well as our advanced technology, which is, hey, we've got this crazy concept. Let's, go investigate, put a prototype together, get it to work. Kind of our research and development wing. But really just from kind of the quick overview here, you can really start to see when we're talking about, a radar array that can be, 25 feet tall down to, smaller munitions, RF systems, electro-optical systems where alignment becomes really critical. We really have, a lot of different domains that we're playing in that our automation has to be able to adapt, and our robotics have to be able to, play in kind of these very different areas across all of our sites. Okay, just quickly, robotics in Raytheon manufacturing, just kind of some general processes. I'll go through these real quick. Assembly. So assembly, inspection, test, kind of the three main categories that we consider in manufacturing. First, assembly, we do have those, franchise, multi-process automation and robotic systems. So, think of your higher volume systems where, we put parts in one end, we feed in a bunch of screws and adhesives and, solder and, big robotic systems that can, basically build a product or sub-assembly up from piece parts to a finished assembly, all through, just pure automation, traditional robotics. We have, kind of recognized that, and you'll hear this probably several times, probably across multiple industries, obviously, but, we have high mix, low volume. And so, really, how do you adapt very expensive kind of, fixed automation to the high mix, low volume world? And one way we're approaching that is through collaborative and process-based modular automation. So instead of having big expensive cell that can do, bunch of different things, bunch of different processes, but it only builds up one product line or one assembly. Hey, what if we move to more of a process-based? So, process-based cell that can do torquing or adhesive or robotic soldering. And then all of a sudden that opens up, hey, if we have a bunch of products that are all a similar form factor, relatively similar size, okay, all we need is new tooling and we can program that, but, we take it process by process versus product by product. And then, end-to-end automation, harmonizing, logistics, material handling, material management. So I think, a lot of times when we think of robotics, it's, a robot building something, it's assembling something. But we have to also look on, what's on the other ends of, that particular assembly cell. We have logistics, and then we have our final sell off, and what do we actually do on each end of that, as well as, okay, how does material get from our logistics area into the cells? And so we approach that through, different things. We have different robotic storage systems with, 6-degree robotic systems on them. We have AMRs, AGVs, or guided vehicles that can actually move product around, which also includes, fully loaded munitions. So we do have AGVs, which is actually the picture in the middle there, that are carrying fully loaded effectors or missile systems. So yeah, that's kind of the degree of confidence that we've been able to build with, particular robotic systems to actually be able to handle energetics. From inspection, we do, final and inline inspection, metrology graded automated inspection. So everything from machine vision to, using high precision lasers, several other methods. And I will say probably inspection is where we use the most AI or ML. And so you can really start to appreciate it when we say, okay, let's take a simple example, a cover, and we have a scratch on it, right? It's painted cover, it has a scratch on it. Okay, we could teach a vision system to recognize a scratch that looks just like this, right? But when you start to consider all of the permutations of what can a scratch look like, it can be deep, it can be curved instead of straight, it can be a squiggle. The depth will, make it look different to the machine vision. That starts to become pretty difficult to program with, traditional machine vision. And so that's where we're really starting to integrate AI ML with a high degree of success. And you can imagine, the risk posture for escapes from some of our products is quite high. So we want to make sure we have every confidence in our automation systems, especially in our inspection systems, that we are building to spec. And then on the test side, using robotics to integrate with test systems. So you can think of it, everything from your basic, we have robots tending particular tests, all the way up to, we actually pick up components, use the motion control of the robot to calibrate different systems within our products. So simple example, an IMU, inertial measurement unit. So we actually use the motion of the robot to teach that IMU where it is in space. Alrighty, some of the challenges that we're starting to see, I think first thing is, as our products get more advanced, we start using more advanced materials, more advanced assembly methods, higher tolerances, higher precisions, exotic materials. So really, they're fragile to handle, maybe. So really, as our products get more advanced, our manufacturing technology needs to grow with that. And that can be a real challenge sometimes, especially when, we don't necessarily have the legacy of manufacturing for new products. So if it's something brand new, that also means our manufacturing has to start from scratch. Our automation does as well. Production scalability and increasing customer needs. So, if you just think of pure capacity, it's one thing to say, oh, we have an automation system that can build this product, and oh, the customer wants to double their production next year. Okay, great. We buy another robotic system, cut and paste. Okay, that's great. But what happens when the customer says, I actually need you to 20x your manufacturing numbers, or it was much more drastic than that even. Now that's not necessarily linear scaling is not your most efficient way to being able to build that and deploy automation. So we kind of have to take a step back and say, okay, instead of cutting and pasting 20 times, really not feasible, even just from a floor space perspective, right? What are some other approaches that we can use robotics and automation to really meet that need? So, not just scaling linearly, but, optimizing. Obviously, low volume, high mix, I think that'll forever be a real challenge for us. Compliance and cybersecurity. And this, really kind of leads into AI as well. When you think of even a basic AI model, an LLM, Well, that has a lot of training and data behind it. Well, we can't necessarily always just use those open source LLMs that are out there. We have cybersecurity concerns, especially when we start to partner the AI with things like machine vision or metrology systems, where we can actually start to glean different aspects of the product from the machine vision or whatever it may be. So challenge for us there. Although we are currently working through that, and we do have AI deployed in different networks across Raytheon. And then legacy design and manufacturing methods, really working towards a shift in how manufacturing is viewed. And so, really from that really industry 2 kind of mindset, going into industry 3 and ultimately industry 4. And that also bleeds into the actual design of the products. And let's see, last slide I have here. So where are we going? As robotics and the defense manufacturing, kind of specifically Raytheon. So just some general concepts here. Self-optimization really leads into the scaling point that I was discussing before. We need our production to be flexible versus static. So static being we have one automation system that only builds this one thing. That's all it's ever done. Now we need to kind of open that aperture a little bit more and make it kind of do multiple things. And if we have multiple of those cells, how do we optimize the flow between different automation and robotic systems? Human robot teaming at scale. So we do have some limited collaborative robotics, and kind of a lot of that comes down to the specs needed out of the robotic system. But we do have more of that, always continuing to grow there. Digital twin driven manufacturing goes back to, we can't think of data and the physical product as kind of 2 discrete entities anymore. Digital twins really helping us merge that. Flexible production and reconfigurable robotics, self-learning and diagnostic. So diagnostic, if traditional robotics, if we have a fault on the system, it'll freeze, it'll say, hey, something's wrong. It'll pause there until somebody can go and address that, whether it's an operator on the floor, a technician, an engineer. Really where we're trying to move is, can the robotic system actually fix and heal itself? And then integrated logistics and robotic handling. So, if we're thinking end-to-end of robotics versus, traditionally it's just been an assembly cell, a test cell, an inspection cell, or maybe a combination of 2 of those. How do we kind of integrate the full end-to-end with robotics? And really the key takeaway here is AI can play in all of these spaces, and it will have to. And so whether it's AI used for optimization or for automatically configuring or the diagnostic portion, AI is going to start to be a key in a lot of these aspects. And I just want to thank everybody for joining today, and feel free to contact me anytime.
All right. So Chris would be our next speaker. Thank you, Blair.
All right, can you see my presentation?
Yes, looks good.
All right, great. So Chris Brown, Technical Fellow in Robotics and Boeing Technology Innovation, based out of Tukwila, which is just south of Seattle. During the overview, been at Boeing about 20 years, been in the R&D space, split between robotics and non-destructive inspection. So just jump in here. Boeing has a long history of robotics and automation. We've been building airplanes for a long time, and automation has been key. Just to start giving an overview of some of our traditional robotic systems. These are kind of the more recent, more advanced systems that are in production today. It's your traditional industrial automation. It is your choreographed NC programmed robotics. It is using industrial safety standards. And as mentioned in the two previous presentations, it's no people in the space when the robots are operating. It's robots are not self-diagnosing. They have an issue. They enter an unknown situation. An operator needs to come in. They need to intervene and restart the system. Building the same large parts over and over again, they're great. They're efficient. However, there are the challenges with anything that is complex, and they have limited intelligence. Drill and fill is one of the bread and butter automation pieces we do have at the company. We have it on defense. We have it in commercial. We have it everywhere. It's a pretty industrial standard. One of the other major components you'll see at any Boeing facility is automated fire replacement. Again, choreographed robots, NC programming. The robot goes through the motion. It's a huge burden to program. It's a huge burden to verify. And once it's set in place, assuming all conditions are the same, it works well. However, again, it does what it does. And once it understands there's some sort of an issue, it stops. It requires human intervention. And yeah. One of the more advanced, again, choreographed automation is inkjet coding, painting. Many of you may have seen some articles of this as it's Alaska Airlines tale. Again, really intricate, a lot of machine controls to do something like this, but it's online or it's offline programming time. It's hours and hours and hours of human intervention. And in order to make something like this happen, it is just a lot of human involved labor. As far as the challenges that we face in aerospace for automation, it's a little bit different than what you'll see in a lot of general automation for manufacturing. For us, it really comes down to the size of what we build and the tolerances that are required and verification and validation required to keep airplanes safe. But individual components that might exist on a 777X, you're looking at 120-foot long wingspan, single parts, scaling the length, and tolerances on some processes down at sub thousandths of an inch. So the scale, again, the size, and when you look at the rate, even though we might not be building components and pieces like what you would see for millions of cars coming off of the line, the rates of our high rate airplane 737 is upwards right now of about 42 a month. However, there are millions of operations on every airplane that comes out. So at those rates, there is a lot going on, and the automation has to bear a good brunt of that. How are we looking at mitigating those challenges and adding intelligence into our process? There's a number of steps. And again, this was echoed in the last two conversations, but it all starts with model-rich data, context-aware programs. You embed not just a standard step file, but all of your process data needs to be embedded in your model. If it's not just hole size, but what fastener goes in, what you're going to be drilling, how you're going to be inspecting, what is happening around it, every aspect embedded within the model, it allows you to start adding in some of the self-diagnostics and understanding, having the equipment understand what the intent behind its job is. Advanced planning and control algorithms, instead of just purely offline programming and adding in choreography, NC programs, and the robot going through the motions, you add in smart planning and control systems, state-based systems that, again, understand what's going on through that context-rich model. You have known safe points that the robot is able to be at. It understands entry and exit points from every location where it's at, and you supplement that with those NC program paths on the back end. But it allows the robot to understand what it's doing, if it was successful, and keeping all of those records and decisions within the process. So this is adding the first layer of intelligence into, let's say a drill and fill system. It knows exactly what it's supposed to drill, what happened. It inspects the data. If there is an error, it logs that, and it knows through a decision tree what it might be able to do next. Another advancement we need to understand, and again, echoed through the last two conversations, is digital twins, virtual commission cells, not just understanding where a robot goes in 3D space, but how it gets there, what is connected to it, what its escape paths might be. And it can understand different scenarios that might play out in the cell and automatically adjust and create paths along, any given set of conditions. This, moving a lot further than just traditional manual NC programs and NC generation. Another one you've heard echoed between Blair and SK is true collaborative environments. Today, you have collaborative robots out in space, but normally that is to relieve the need for safety cells, safety things. And the whole point of most of the cells is to have a robot working and a human working fairly close by, but to mostly avoid themselves. One of the jokes one of my coworkers tells is, rarely or never would you come home and say, I had a very successful day at work. I didn't hit anybody, and we worked separately off to the side. So in order to enable a higher mix of human and robotic integration in the same space, we need to add intelligence to better understand what a robot is good at, what a human is good at, and actually work closer in the same space as opposed to just using area scanners and safety sensors and partitioning off spaces. One of the big uses that we have been implementing quite a bit of, and kind of the first pass into AI ML space, is using vision systems to add robustness into processes. Everybody is familiar with general machine vision. You have geometric pattern matching, shape matching, manual taught things, and you might have a high standard deviation when you're trying to locate parts or holes. When you add in neural networks, ML, AI, we've been able to, again, increase confidence, lower the standard deviation of errors by significant margins, and just add in, again, that layer of robustness to help with this. The next steps that we've been working through ARM and other collaborations is leveraging AI ML generation capabilities to supplement training data. One of the major situations for creating any of these data sets in a manufacturing space like aerospace is we don't have a ton of data in order to feed these models. We have a limited manufacturing subset, but if we can create some real images, let's call them deep fake images to supplement training data, then we've had good success with models to actually validate that, increase the teaching subset, and again, increase robustness. The big focus through our organization with all of these measures we're looking at is increasing automation robustness and just removing the need for humans to engage on any single thing and improve the decision making. But yeah, that is what I have for my presentation. Thanks for listening, and yeah.
Wonderful. Thank you, Chris. It's terrific.
Thanks, Chris.
So now we've got some nice time to have a discussion with our panelists. Everyone can start adding their questions to the chat. I'll be going through those and then passing these questions along to our panelists. And while I'm waiting for you, everyone, to start putting a few in, I have a question or two of my own that I'll start with. I think I'm going to pass it out to the panel in general. But you all brought different perspectives to this. Maybe we could start with we talked about gathering data. Could you give a sense of what volume of data is needed for some of these physical AI tasks that you've presented? I know every task is unique, so maybe you could give that with an associated example, but could you give us a sense of how much data you need, how much synthetic, how much real world data you need to get something that could actually operate in a real environment?
Sure, I could go first. So some of the assembly and disassembly skills that we are building at each individual skill level, for example, let's say you needed to learn how to pry out a battery, which is held by string, right? So let's just say very narrow task there. And you want to be relatively general with respect to battery size and the housing conditions and so on and so forth, right? So in that case, you are looking at probably 100 or so physical demonstration, where a person, for a wide variety, it's not just single battery, right? So you take C, AA, AAA, different kind of batteries, different colors, roughly 100 demonstration. And using that, then you can learn that skill quite robustly. Now, if you're trying to do composite defect detection, you will need a few thousand physical images and few tens of thousands of synthetic images to be able to do training to learn how to do defect detection. But that just gives you two representative examples of how much data is necessary.
Yeah, and I would say from machine vision perspective, that's probably one of our challenges, right? Is I can resonate with the SK thousands, 10,000s, but obviously the more the better. But when you have expensive parts and you only have a limited number of what is a defect, that can be a challenge. And so the way we typically approach it is through using a confusion matrix or something similar, which can evaluate your essentially looks at what are your false positives, what are your false negatives, where are you starting to converge on, hey, we're adding more and more pictures to our data to our model, but we're not seeing an incremental increase. And so we'll use a couple different methods along those lines to eventually say, hey, this is good enough, or this is as good as we're going to get. But then we also do continue to capture. We'll put something into production, continue to capture pictures, and train the models. So I guess it kind of depends, but we do have tools at our disposal that can help us show, hey, when are we starting to reach a high level of confidence for the AI system? At least that's how we use it in machine vision.
Yeah, and to echo similar use cases for what Blair is mentioning, except we have a tendency to also in the beginning bound the problem down to a simpler issue in the beginning, and then as you build that data set, you can expand it, add a little bit more uncertainty to it. But it's always going to be a challenge in an aerospace and manufacturing environment for capturing data like that in the beginning, and it's always going to be hard.
Excellent. Thank you.
Yeah, if I may, I have a follow-up question. That's also for all three of you. So how deep is the data that you use? What I mean is that data can be geometric data, can be kinematic data, can be even force data. Let's say for the grinding operation, obviously have the shape data. What about the grinding force and all that? When you train your AI model, to what extent do you use the data to train your model?
So again, let's dig into the grinding example, right? So there are many different phases of it, right? So think about if you want to do autonomous grinding, you want to take a complex geometry, you want to break it down into regions, and then you want to basically generate path for each region, and then you want to regulate process parameters. So you're doing so many different things, and each of these tasks require different kind of data, right? Obviously, when you are making a contact and regulating the process, force data is super crucial, because without that, you will not be able to regulate the process the right way. On the other hand, when you're looking at complex geometry, trying to decompose into segments so that you can see the right kind of features and then start planning there, it is largely 3D shape that need to be decomposed. So there, it's the shape which plays a role. And then, of course, when you're trying to monitor it for defect, then image becomes super important, right? So you record all the data, and then depending upon the task that you're trying to do, right from approach to generate the path, to perform the grinding, to do the inspection, you use the relevant data. But you collect everything, right? You collect the information about the shape, the vision, the force, the RPM, the process condition. You collect everything, and depending upon what you're doing, you use the right kind of data for that task segment.
Great, thanks. We've got some questions piling up here in the chat. I'll share a few of them. One of the questions is commenting on, and maybe I'm going to try to paraphrase here a little bit to capture it, but so the idea is that you're using these tools, this physical AI tools, to train. Somebody observed that they've seen, though, that when these get in place, I'm assuming that they continue to train while operating, and sometimes they degrade in performance. Is there a way you manage that? Do you lock in a fixed system and go back to maybe a traditional control of the robot once it's actually in a production system? I guess maybe the question is, when do you know that you can transition to production and to be confident that it will maintain the quality that you saw? Do you stop the learning? How do you manage that, I guess, is what I'm reading into that question.
I can say for us, once we put something into production, when it's certified, when it's qualified, we would not let it self-learn throughout the production, but we would still collect data. And then when there is an implementation point, we can revalidate, recertify, but we would have to validate that, again, you aren't hallucinating and the quality isn't getting worse. But we don't let the process go on an open loop, just learning in production. That's not what we can allow to happen quite yet.
Yeah, just to further amplify what Chris said, I mean, there's a training phase where you collect the data and train the system, and then you freeze all the learning and you deploy it. And but even when you deploy it, you need to basically build out of distribution detectors to make sure that the data on which you're going to make decision is not out of distribution. Because if the data starts coming in and it does not look like at all the training data, you want to shut down the system. Not only you don't want to learn, but you also want to start putting guardrails to make sure that in the field, if you start encountering data which looks alien to you, not only you don't learn from it, but you don't use it either, right? You want to, at that point, simply stop and saying something is odd here, right? So an example is that, for example, let's say you're trying to do image-based sandpaper life prediction, right? And you have accumulated significant amount of dust on the lens, and therefore your image quality is now different, right? So you want to have an auto-distribution predictor, which will tell you that, okay, your lens is not clean. So you should not be trusting the data at all, basically, which is coming from it at this point, right? You want to shut down the cell, get an operator, clean the lens before you even make a decision on it, right? So not only you want to not learn in production, you also want to put enough guardrails there to make sure that you don't create a mess in production.
Excellent,
Yep,
thank you. Go ahead, Blair. Go ahead.
Yeah, just one thing. One approach we've kind of done is we can validate some of our AI solutions using more traditional methods. So if we, one example, we've used AI in some circuit card manufacturing. Well, then we go and put it through your traditional AOI, your automated and optical inspection system, which is on every surface mount manufacturing line that's out there, super proven in technology, very reliable. So we're actually validating some of our AI with more traditional systems. And that's one method we've used. Kind of catch and make sure that we're still operating within parameters.
Terrific, thanks. I think you guys actually captured what we were trying to get there, so thank you. Okay, so another question. Do you have some advice on maybe perhaps this is for young people that are like engineering students or very early career people coming into the field? Do you have some advice on what specific interdisciplinary skills students or early career people should be focusing on to be competitive in an AI-driven manufacturing sector?
Well, maybe we had a professor on the line.
Yeah.
I can speak from kind of Raytheon perspective. I would say, we really have all backgrounds in our organization. I'm mechanical, but I would say that anything in the AI space, we have a lot of folks taking certificates for AI work. I know there's some kind of more control specific degrees out there, but we have electrical engineers. So I think it's really about advancing yourself through the opportunities of certificates or maybe not full-time degrees in the AI space or robotics, but there's quite a few options out there. And then from a controls perspective, we offer a lot of on-the-job training, sending folks to PLC courses and robotics courses, and obviously AI, machine vision. So I think starting to immerse yourself in a lot of the additional resources, and a lot of it's free out there, which I think is something that is relatively new. But my perspective is less about the degree, but more about how do you immerse yourself in where you want to go with automation.
Yeah, and in a similar vein, I would say, as these worlds of automation, mechanical engineering, and computer science are starting to get more merged together and linked, you're already seeing more students coming out of the universities with engineering degrees, but a lot more comfortability with Python, with scripting, with using these tools. And again, it's not the degree they have. It's not what's necessarily on the resume, but it's just the comfort using these tools to enable increased efficiencies and capabilities. It's different than it was 20 years ago, but it's always, stay current, stay involved with, as Blair said, certificates, learning, and staying on the cutting edge. But it's just kind of a merging of the kind of hardware engineering and software engineering at this point a little bit more.
Great. Thanks. Okay, another question from the chat, quite a few here. Chris, you had discussed using expanding your physical gathered images with images generated through AI for training, or artificially generated or synthetically generated images. So there's a little bit of a concern about using these generated images that would negatively impact the quality of the training. Perhaps, so, just kind of discussing using these artificially generated images along with the others. And then I might add to that, then how do you then at the end meet your quality requirements or your certification requirements that you can deploy this system?
So far with our testing at a lab level, we have seen only positive increase in confidence with using the synthetic data. If you are seeing a loss in quality or confidence, then you might need to pivot what you're using to create that synthetic data. But once it comes to validation in the real world, it's the same validation, the same understanding as you would use with a full real data set. It's just a matter of using it to supplement the data and to, again, try to add robustness in that training set. But so far, we've actually had pretty good success using a decent image engine to create that data.
Yeah, and our experiences are exactly the same, right? So boosting to training pipeline with carefully generated synthetic data helps quite a bit. All your validations are done in real world. It's just that you want to make sure that your image generation pipeline is correct. And there are two popular ways to generate images right now. One is that you set up your your physics-based pipeline to introduce. I'm only making remark in the defect context to generate defect, then basically physics-based or physics-informed pipeline to generate photorealistic images by simulating all the light interactions and everything, which gives you pretty good photorealistic images. So that's one way to do this. Sometimes that's not possible, so then you can use Gen AI, diffusion type of methods to generate synthetic images as well. As long as those pipelines are, again, controlled well, then it becomes very useful. And one thing that we did not discuss, see, when you have physical images, they require labeling. And sometimes physical image labeling is such a challenging task that you may have images, but you do not have manpower to label them. And that creates a huge problem. Once you have synthetic images, they get auto-labeled, right? So you usually build the capability to auto-generate the labels for your synthetic images. So that's the reason why that becomes very useful capability, particularly when we're talking about defect type of scenarios, right?
Excellent, thank you. Okay, there's another line of questioning around safety. I know you discussed it, some industrial safety standards at different times, but this particular question says safety has always been an issue, in particular in the PHRI or the physical human robot interaction context. Introducing AI and task planning for physical control, reactive control brings up the necessity of certifying a system. Could you talk to us about how you go about certifying, how you explain that you understand what's going to happen, and basically how will this interact with the existing industrial safety standards?
I mean, I would say that is a great question, and why right now when we use collaborative robotics, we use industrial safety sensors, and it's mostly limiting the interaction between them because that is a very challenging topic to actually solve and to get bought off in industrial safety, and we're still trying to understand that ourselves. But if whoever asked the question has any great ideas or advice, that would be great. But yeah, it's a really challenging one right now.
Yeah, I'm just gonna amplify Chris's messages right now. When you are trying to learn a lot of basically learn component, you really want to have the safety in place so that when robot is doing things, humans are not close to it, right? And therefore, you have appropriate machine guarding, appropriate cell setup so that human cannot go close to the robot when robots are operating. Obviously, that makes the cell a little bit less collaborative, but right now, that's a challenge that people face because when robot is working in high mix, you cannot simply say that, okay, I ran this program before and I knew exactly what happened, right? That luxury is not there. It's a new part. Robot is going to sense it and it's going to generate a brand new, motion plan to execute it, right? So it's kind of difficult to certify it using traditional methods. So yeah, so that is a challenge and that need to be looked at it in terms of collaboration perspective. But as long as you have your machine guarding there and humans are away from it, nothing prohibits you from using a learned model to execute, right? So,
yep. And then when you think about the hierarchy of robot control, right? Safety is at the very top, even if you have, an AI control system in there. Even just simple things like your DCS on FANUC robots, which basically tells you what envelope can the robot work in. Always have those types of controls at the very top. You can never go outside of that. You can never ignore safety sensors, things like that. That can obviously help limit things, but at the end of the day, if it's an industrial robot, they're powerful and can be very dangerous. So whether you have an AI layer in there or not, still need to observe a lot of those safety standards.
Thanks, Blair. Thank you. Okay, we're coming to an end. I might just ask one last question to the group. If you could look into your crystal ball, say for the next 5 years, what you see is the next big thing that you would expect we would see in your respective industries in physical AI for robotics. If you could just maybe make a quick prognostication on that, we'd be interested to hear.
I would say just improved ability for the automation to take on a little bit more of the decision making that a typical trained operator would make. So adding robustness to the process through, again, contextually aware models, through teaching, and instead of having to have an operator intervene in so many different unknown scenarios, you add the ability for the automation solution to make some of those decisions, and then you can increase some of the numbers that SK was showing on how many operators per machine are out there. At least is where I think we're going to go, and where I would like to go personally.
Yeah, I'll probably give two answers. The kind of the pessimistic answer would be, the robots that can use AI for optimization and adaptability. So that, really, speaks to a lot of what SK showed during his presentation. We can throw anything at a robot and it can, we say sand, and it can figure out how to sand that part. And then optimistically, the advancement of, your humanoid robots, so your Teslas and your Figure AIs, it's really grown so exponentially in the past few years. Figure AI is already in manufacturing spaces. We're partnering with BMW and quite a few other companies. So, I could see some kind of specific use cases in the future, maybe around material handling and logistics. But I think, the humanoid space really excites me quite a bit.
Yeah, I think overall I see, robot applications increasing more. So we began this journey with purely material handling robot, then inspection matured, then we are now looking into surface treatment, surface application, modification type of things. We are seeing some exciting stuff in assembly. We will continue to see, further up the value chain in terms of process difficulty, where robot will be able to work in high mix applications. So that's the trend line that I see right now.
Excellent. Thank you. Well, with that, we've reached the end of our webinar. I very much appreciate everyone attending. There's definitely, this is a clear pivotal shift going on in manufacturing, and it's exciting to see. I would encourage everyone, if you can raise a emoji hand or a similar reaction for an encouragement for our panel. I want to thank our panel and very much. Wonderful. Oh, this is awesome. Want to thank our panel and also thank the editors and ASME for sponsoring this. Again, if you have research work that you want to share, please reach out to our editors and consider ASME robotics journals as avenues for that. Thank you again, everyone. Thank you for your time. Terrific webinar.
Thank you.
Much.
Thanks. Bye.
Yes, bye.